In this video, we're going to take another look at finding equations of rational functions. Now that we've learned about slant asymptotes, we can talk about ones that have slant asymptotes in them as well as we're going to review all the concepts from rational functions. So we've previously learned how to create the equation of rational functions from information about its asymptotes, but now we're going to see how the slant asymptote plays into that. So an example here, we're going to do both of these ones, the one on the left and the one on the right. The directions say find an equation of a rational function that has, and then they're going to give you a bunch of information. So we've already talked about the denominator is going to be made of numbers that cause vertical asymptotes. So the very first thing you always want to start with are vertical asymptotes. In this particular problem, they're telling us the vertical asymptote is at x equals -2. That means a factor from the bottom has to be x plus 2. So remember, vertical asymptotes tell us about the denominator. Removable discontinuities would be factors that show up in both the numerator and the denominator. But because this example says it doesn't have any removable discontinuities, we don't have to include any factors on both the top and the bottom for this example. Horizontal asymptote in this problem says none. So what that means, what we now know, is that the numerator has the bigger powers of x compared to the denominator. And then as we look below that, we're not just allowed to put anything that we want in the numerator, because now they're saying that the slant asymptote is y equals x minus 6. Now remember, the opposite of the way you find a slant asymptote is by dividing the numerator by the denominator. So the opposite of that, if you're trying to build the function back together again, is to multiply the denominator, which was x plus 2, times my slant asymptote, which is x minus 6. So if you multiply these together, you're going to get x squared minus 6x plus 2x minus 12. So we have, if you collect like terms, we have x squared minus 4x minus 12. Now the trouble is, if I put this into my numerator exactly the way it is, that means that the top and the bottom have a common factor of x plus 2, which would cancel out and make a removable discontinuity. So what that means is this equation, this expression that you're seeing, x squared minus 4x minus 12, can't be exactly what my numerator is, because that would cause removable discontinuities. Remember that when we're doing slant asymptote, there could have been a remainder that we had to throw away. So what you want to do here is you want to modify the constant at the very end of this by just a little bit, so that it won't factor and reduce the fraction. In other words, what I'm going to use here in my numerator is going to be x squared minus 4x minus 11. You don't have to pick 11. It could have been any number but not 12, because if you use 12, this factors and reduces and creates removable discontinuities. So we're using multiplication. We're multiplying the slant asymptotes equation, x minus 6, together with any other factors in the denominator, and then we want to modify the constant just a little bit so that it doesn't create removable discontinuities that we don't want. All right, let's try one more example of this. In this particular problem, they're telling me for vertical asymptotes that there are none. Now, what that means is that when they say none for vertical asymptotes, that means they must have been imaginary. The simplest thing that I can think of that causes imaginary answers is x squared plus 1. So as I go to build my fraction here, I'm going to start off with, in my denominator, x squared plus 1, because I know that creates imaginary roots. They also tell us that we have a removable discontinuity at x equals 5. So that's a factor. X minus 5 is a factor that must be showing up in both the top and the bottom, because removable discontinuities, of course, show up in both places. And then last but not least, we have a slant asymptote. We don't have any horizontal asymptotes, so that means the top is bigger than the bottom by 1 degree. And we have a slant asymptote that is y equals 2x plus 1. So in order to help me fill out the rest of the numerator, I've already got the x minus 5 up there. I'm going to need to multiply my x squared plus 1 times my slant asymptote, which is 2x plus 1. Again, that's going to produce 2x cubed plus x squared plus 2x plus 1. And that's what I'm going to want to add into this numerator right here as a multiplying factor, 2x cubed plus x squared plus 2x. But if I put it in exactly like it is, that means there would be a reducing between the numerator and the denominator, which we don't want. So I'm going to modify this constant just a little bit. Instead of saying plus 1, we could say plus 2 or plus 3 or whatever other number that you want, but not 1, so that it doesn't factor and reduce. So I'm going to put a plus 3 there. Again, you could pick a different number if you'd like. So this fraction now contains all of the elements that we're looking for. It will produce the right removable discontinuity at x equals 5. It will produce no vertical asymptotes because my denominator only is 0 when it's imaginary or 5, and 5 is the removable discontinuity. And then the numerator is made of the product of my denominator that's not the removable discontinuity times my slant asymptote with a modified constant so that it doesn't reduce. So that's how you do problems that have slant asymptotes and you're trying to find the equation from all of that information. Okay, at this time now that we're done with that, we're going to take a look back at the entire chapter. I know it's only been a few days worth of notes, but it's worth looking over one more time. So remember that the definition of a rational function is a function that's built of a fraction of two polynomials, p of x and q of x. And what we ideally want here is for p of x and q of x not to have any common factors. We don't want them to reduce. If they do reduce, they will create a removable discontinuity, which is going to be represented by a hole in the graph. So if you factor p of x and q of x and you notice there's factors that are going to cancel each other out, you're creating holes in the graph, and those are called removable discontinuities. The next thing that we have to remind ourselves is how to find asymptotes. Vertical asymptotes are found by setting the denominator equal to 0 after the rational function has already been reduced. So if there were common factors, you've already got the removable discontinuities taken out of there. Now whatever's left over that makes your denominator go to 0, that's a vertical asymptote. So for example, in this problem, the numerator, when factored, is x minus 3, x plus 3. And the denominator, when factored, is going to be x minus 3, x plus 2. And you're going to notice that the x minus 3's here cancel out. So really, the only one that's creating, by the way, x equals 3 would be your removable discontinuity in this example, but we're talking about vertical asymptotes, and the vertical asymptotes would only be caused by that factor. So your vertical asymptote would be x equals -2, only -2, not 3, because at 3 you've had cancellation, which creates a hole in the graph. Okay, the next thing that we're going to talk about are how to find horizontal asymptotes. Remember, horizontal asymptotes are found by playing a little game. It's called who's got the bigger powers of x. If your numerator p of x has a degree that's bigger than your denominator, your horizontal asymptote will be none. If the bottom part of your fraction, your q of x, has the bigger degree, then your horizontal asymptote will be y equals 0. And if they happen to have an equal degree, then what you're going to do is set y equal to the ratio of the leading coefficients. All right. The third type of asymptote that we've just recently learned about is a slant asymptote, and those occur when the numerator's degree is exactly 1 larger than the denominator's degree. And the way that you're going to figure out your slant asymptote is by doing division, and you're going to throw away the remainder. What type of division you do is based on what kind of divisor you have. So in this problem, since I have a linear divisor, x minus 4, I would get to use synthetic division. And I would take advantage of that anytime I can, because we know synthetic division is a lot faster and easier. So my coefficients in the numerator are 2, 5, and -7. So if I drop the 2 down, 2 times 4 is 8. Add this together, you're going to get 13. 13 times 4 is 52. Add that together with the -7, you're going to get 45. If there's a remainder, we simply just throw it away, and we make our equation for our slant asymptote out of setting y equal to our quotient part, which in this problem would be 2x plus 13. All right. Next, we want to talk about how to graph a rational function. That's probably one of the biggest things that we have to do in this unit, is understand the way these graphs look. We always start by finding the y-intercept, and you do that by setting the x value equal to 0. The next thing you're going to do is find the x-intercepts, and you do that by setting your numerator equal to 0. The next thing you're going to do is check for removable discontinuities. You basically want to factor the top and bottom to see if there's any cancellation. If there is cancellation, any place where it cancels, those are going to be your removable discontinuities. If there isn't cancellation, you would just say none for that. The next step would be to find all the asymptotes, the vertical, the horizontal, and the slant asymptotes as we previously described. If there are those kinds of asymptotes, you're going to want to draw those on your graphs as dotted lines. They're not actually part of the graph, but they're going to guide the way that you make the graph. And step number 5 is to make an x and y chart and pick x values from both sides of the vertical asymptotes until your graph becomes clear. Now, how many points that takes depends on your level of experience with these. At first, you might need a lot of points because you've never seen these types of graphs before. But as you get more experienced with rational functions, you'll start to need less and less points in that chart because you'll start to see like, oh, if I have to get close to this dotted line and this dotted line, and I've got these couple of points already, then my graph's got to look like this. So it'll get easier the more of these that you do. Just make sure you label everything, the asymptotes, the graph, the x and y axis. Put a scale on your graph so I know how big you're talking about in each one of the directions. And then last but not least, if somebody's going to ask you to find a rational function from knowing information like the asymptotes and the removable discontinuities and all of that, that's what we just practiced with at the beginning of this. You're going to use your vertical asymptotes and your removable discontinuities to determine the denominator. Vertical asymptotes are factors that only occur in the denominator, and removable discontinuities would be factors that occur in both the denominator and the numerator. So you want to make sure you're putting them in there. We always start with the denominator first. And then we're going to use the horizontal asymptotes and the slant asymptotes to help you determine what the numerator needs to look like. Now, the horizontal asymptote just gives you an idea about the degrees, the comparison of the degrees. And if they happen to be the same degree, it would give you an idea about the ratio of the leading coefficients. If there's a slant asymptote, you would have to multiply the slant asymptote's equation part, the mx plus b part, times whatever your denominator is to help you find the numerator. But remember, you don't want it to be exactly factorable and cancelable with the denominator, so you have to modify the constant just a little bit so that it won't reduce and create removable discontinuities that you don't want. So we've already done a couple of examples of that today, and that's a review of our entire rational function unit. You're now ready to try the homework for tonight.